So chapter 10, section 1, in this we'll determine the null and alternative hypotheses. We'll explain what a type 1 and type 2 error is, and that's more a vocabulary or understanding. And then we'll state conclusions to hypothesis tests. So a hypothesis is a statement regarding a characteristic of one or more populations. Okay, in this chapter, we'll look at hypothesis regarding a single population parameter. All right, so looking at this, here are some claims regarding a characteristic of a single population. And I'm not going to read all of them, but I'll read one. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So that's a claim based off of a single population, American adults, right? So that's just another. And here's the last one. I'll look at the last one. Using an old manufacturing process, the standard deviation of amount of wine put into a bottle was 0.23 ounces. With the new equipment, the quality control manager believes the standard deviation has decreased. So you can hypothesis or perform a hypothesis test on this to be able to either accept or reject the null or alternative hypothesis. So if population data are available, there's no need for inferential statistics. Okay, just kind of know that. Hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding characteristics of one or more populations. We're going to do a single population, so we don't have to worry about anything. Steps in hypothesis testing: make a statement regarding the nature of the population, collect evidence to test the statement, and then analyze the data to assess the plausibility of the statement. So that's basically what we're going to do. Okay. A lot of this stuff that we're doing is just kind of theory and just kind of leaned up. The null hypothesis, denoted H0, is a statement to be tested. The null hypothesis is a statement of no change, no effect, or no difference, and assumed true until evidence indicates otherwise. So the null hypothesis, and we're going to look at this, the null hypothesis is going to be basically no change, right? Nothing. It's going to equal no change. Nothing has happened to it. So, and then the alternative hypothesis, denoted H1 or H sub A, depending upon what book you're using or have used in the past, is a statement we're trying to find evidence to support. Okay, so those are your two that we're going to do. We're going to note a null and alternative hypothesis, H1 and H sub 0. Okay, now there are three ways to set up the null and alternative hypothesis, and we're looking at a two-tailed test. What I mean by two-tailed is basically that's a two-tail, right? We're looking at a normal distribution. It's the area left and right of a curve. Of course, left tail, if you think about it, that's going to be, let me use this, on the left side, right? And then a right tail test will be area over here. Okay, so drawing these, this is what each one looks like, right? Now, if you'll notice, the null hypothesis for a two-tail, left tail, or right tail test, the null hypothesis always has a equal equality in it. And what I mean by equal equality, it's going to equal some value. Now, you could have this, less than equal to or greater than equal to, and we'll talk about that because the null hypothesis is supposed to be the opposite of the alternative hypothesis, right? So it'll make sense, but it's always going to have an equals, okay? Now, when your alternative hypothesis, when there's no change, it says, there's doesn't think it changes anything, then there's your does not equal. If it says it's greater than or less than, then will be a left tail or right tail. Greater than for a right tail, less than for a left tail test, okay? So why is that important? Well, we're going to look at doing a hypothesis test for population proportion, and we're going to look at it as a classical, or we look at it as a p-value, and then really we'll just kind of look at those two, but we'll do it on the calculator, which will give you both of those answers. It's a little less complicated than what the notes and examples are going to show. Okay, so in other words, the null hypothesis is a statement of status quo or no difference, and always contains a statement of equality. Said that. A null hypothesis is assumed to be true until we have evidence of contrary, and we seek evidence that supports the statement in the alternative hypothesis. Yeah, we got to find something to support the alternative. All right. Any questions on these three tests? What they mean, a two-tail, what it looks like, what a left-tail test looks like, what a right-tail test looks like. Anybody? All right. So we'll carry on. Forming hypotheses, and we'll look at this. For each of the statements, determine the null and alternative hypothesis, state whether the test is two-tailed, left-tailed, or right-tailed. Okay, so we got to make sure we can know, all right, what type of test are we going to be doing? So in 2008, 62% of American adults regularly volunteer their time for charity work, right? A researcher believes that this percentage is different, right? Well, the null hypothesis, H sub 0, means that there's no change, right? So we're looking at P equals 0.62, right? Now, because we're saying, okay, 62% is no change. The alternative, H sub 1, is stating that, okay, it didn't say, it just said it's different, right? The researcher believes it's different today. It didn't say it was less than, it didn't say it was greater than. It just said it was different, right? So when it says it's different, it means it's just not equal to 0.62, right? And if you look on the previous chart, well, this chart, you can see where it says the null equals and the alternative is not equal is a two-tailed test, right? So this is how a two-tailed test is an example of how it would be presented. And of course, I put the solutions down here so that you could see it as well. Okay. Any questions on that? All right, so let's look at another one. On this one, again, we've got to tell whether it's two, left, or right, okay? And if it's two, we're looking at no change, right? And if it's left tail, then we're looking for something that says less than. And if it's right tail, then we need greater than, right? Those are some keywords, or more, or increase, or such. So according to a study published in March 2006, the mean example, or the mean length of a call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. Okay, so note that we're talking about the mean, Okay, on the previous question, we were talking about population, right? We talk about it, the adults as a population. That's why we use P right here. Okay, that's why we use P there. Now this one, in this example, it said, hey, the mean. So that's why we'll use the null hypothesis as being the mean equal to 3.25, meaning it's 3.25. It has not changed, right? Now, the alternative hypothesis means that the mean length of call is increased, right? Which would be a right tail. So the mean is greater than 3.25 minutes, and it's a right tail test. Okay, now that's going to be important when we start to use the calculator to be able to know what tail test to be able to perform the hypothesis testing on, right? So just kind of know that there's keywords in, and we have to know the difference between them. All right. Note that even on this example, the null hypothesis had no change, right? It was exactly what was stated, right? Whatever this initial statement was. Now we're going to be able to test these in the next section to be able to determine whether we reject or accept the null or alternative hypothesis. Okay. Let's look at C. So using old manufacturer process, the standard deviation of the amount of wine was 0.23 ounces. Okay, with the new equipment, the quality control manager believes that the standard deviation has decreased. Okay, has decreased. It's less than, right? So this would be a left tail, all right? So, and note that they said standard deviation, okay? So we know that the null, that standard deviation of it was of wine in a bottle is 0.23. So we're going to say null hypothesis is no change. It is standard deviation equals 0.23 for the null hypothesis. Now, when we do the alternative hypothesis, we're looking at, because the quality control manager believes that the standard deviation has decreased, then we're again looking at a left tail, right? Less than, right? So we're looking at the alternative standard deviation, alternative hypothesis standard deviation is less than 0.23. Now, we just did 3 examples of looking at null and alternative hypotheses. We looked at a population, we looked at a mean, and we looked at a standard deviation. Okay. And for 2 of these, well, really for all of them, but for 2 of them, I pointed out the word standard deviation, the word mean, right? The mean there. And then if it doesn't have any of them in it, then it's talking about a population. Okay. And that would be why it's P. So there's, besides doing a left tail, right tail, 2 tail, you've got to also know that there can be hypothesis testing, right, and a null and alternative for a population parameter, for a mean parameter, and a standard deviation. Okay, so you would look back at the initial claim and the stuff to be able to find which one we're talking about. Okay. Now, 4 outcomes for hypothesis testing. Now, these are things you need to make sure that you have written down, okay, or quickly accessible. If you reject the null hypothesis, or you reject the null hypothesis when the alternative hypothesis is true, right? So we made a statement, we made a claim, and we're going to test it. If it comes out to be a true claim, then we're going to accept the alternative hypothesis and reject the null, right? Do not reject the null hypothesis when the null hypothesis is true. This decision would be correct, right? If the null hypothesis is true, we can't reject it, right? Now, reject the null hypothesis when the null hypothesis is true. This decision would be incorrect, right? This type of error is called type 1. Okay, so we're going to reject for type 1 error would be to reject the null hypothesis when the null hypothesis is true, meaning the claim or statement for the alternative hypothesis can't be proven, but we still reject the null, right? That's a type 1 error. Do not reject the null hypothesis when the alternative hypothesis is true. This decision would be incorrect. The type of error is called a type 2 error, right? So not rejecting the null hypothesis when the alternative hypothesis is true is a type 2 error. So knowing what condition gives you a type 1 or type 2 error, those are the key things, okay? So any questions about that? Anybody? Any questions? We good? Yeah, no chats. Check and see how many people. We got 11 people on here. Yep. Okay. All right. So type 1 and type 2 errors, we just got some examples to go through. For each of the following claims, explain what it would mean to make a type 1 error. So what would it mean to make a type 2 error? So in 2008, 62% of the American adults regularly volunteer for their time for charity work, right? We're using those 3 cases, again, that we looked at in the beginning. The researcher believes that, that the percentage is different today. So for a type 1 error is made if the researcher concludes that the alternative hypothesis that P does not equal 0.62 when the true proportion of Americans 18 or older who participate in some form is currently 62%, right? So if you look back, we said what? Reject the null when the null hypothesis is true, right? That'd be a type 1. So saying that it's not equal to 62 when there's nothing that is showing that it's different, okay? Now, type 2 errors made in the sample evidence leads the researcher to believe that the current percentage of Americans of 18 or older who participate in some type of charity work is still 62%, when in fact it differs from 62%, okay? So still holding on that the null is true even though the alternative is true. That's a type 2 error. Example B, according to the study published in March 2006, the mean length of a phone call, that the researcher believes that the mean length of phone call has increased, right? So a type 1 error occurs if the sample evidence leads the researcher to conclude that the mean is greater than 3.25, when in fact the actual mean call length on a cellular phone is still 3.25, right? And a type 2 error occurs if the researcher fails to reject the hypothesis that the mean length of phone call is 3.25 when in fact it's actually longer, okay? So how am I going to be able to keep or understand what a type 1 and type 2? Well, you need to make sure that type 1 error, that reject the null hypothesis when the null hypothesis is true, okay? Rejecting it when it's true, that's type 1. And then not rejecting it when the alternative hypothesis is true would be a type 2 error. So, all right, so alpha is equals P, type 1 error is rejecting the null when the null is true, right? Type 2, not rejecting the null when the alternative is true. So this kind of, I guess, this right here, alpha and beta, would probably be a lot easier to grasp. I would kind of have that on a note card or something like that, so I could quickly reference for a type 1, type 2 error, okay? Now, the probability of making a type 1 error, alpha, is chosen by the researcher before the sample is collected. So there's the level of significance, alpha, is probability of making a type 1 error, okay? So a type 1 error is the same as the alpha, which is the level of significance. Now, what's important about the level of significance, right? Well, we did, what did we do? We did confidence intervals, right? So an alpha is equal to 1 minus a confidence interval, right? So 1 minus a 0.95 confidence interval, the alpha would be 0.05, right? So they go hand in hand. They're related. Alpha is 1 minus the confidence interval, okay? So if you're looking at an alpha of 0.05, then you're dealing with a confidence interval of 95, okay? So that kind of ties in where we were at in the last chapter. So let's look at this other relationship. As the probability of a type 1 error increases, the probability of a type 2 error decreases, and vice versa. Okay, they're inversely related. All right. Any questions on that? All right. So let's see what we got next. Here's a caution. We never accept the null hypothesis because without having access to the entire population, we don't know the exact value of the parameter stated in the null. Rather, we say we just do not reject the null, right? We either reject it or do not reject the null. Okay, we can't say we accept it. This is like the court system. We declare a defendant innocent, but rather we never declare a defendant innocent, but rather we say the defendant is not guilty. Okay. We can't accept the null. We can only reject it or not reject it. Okay. Big thing right there. That's one of the last things to kind of hang our hat on before we leave this section. All right. I thought we didn't have any more, but I guess we do. Okay, so according to a study published in March, we're still on these. So, okay. Suppose the same evidence indicates that the null hypothesis should be rejected, stating that the wording of the conclusion. The statement in the alternative hypothesis is that the mean call length is greater, right? So we're looking at how should we write it, right? How should we state it if they come back and say, okay, the sample evidence says that the null hypothesis should be rejected. That means that the alternative hypothesis was true, okay? So the statement in the alternative hypothesis is that the mean call length is greater than 3.25. Since the null hypothesis, the mean is 3.25, is rejected, there's sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25. Sufficient evidence, right? So they're just giving you examples on how do I state it after I find whether I accept or reject the null hypothesis and accept the alternative. Okay, so this is basically what these two examples are doing. And we'll look at this one. Suppose the evidence indicates that the null hypothesis should not be rejected, state the wording of the conclusion. Since the null hypothesis, the mean is 3.25, is not rejected, there's insufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes, right? That was our alternative hypothesis. That was our claim, right? In other words, the sample evidence is consistent with the mean call length equaling 3.25, all right? Meaning we rejected the alternative and accepted the null, right? So that's just some verbiage on kind of representing how do we display our answer, how do we answer the question when we do it, because we're about to do some testing here in 10.2 and then make a little bit more sense, okay? All right, so that's all of 10.1. Okay, so when we looked at it, we're talking about, okay, what is a hypothesis? We looked at what type of populations we could perform a hypothesis test on. We also looked at creating the null hypothesis and the alternative hypothesis. We looked at a left tail, right tail, and two tail, right, based off of the null and alternate hypothesis. So with that being said, and we looked at type 1 and type 2 errors, and then how to represent the final answer. That's kind of nutshell in 10.1. We look at its homework. The null and alternative hypotheses are given, right? The null is always going to have an equal, right? So if you look right here, here's your hypothesis, here's your null, right? And then there's your alternate hypothesis. And the null will always have an equal to, right? And some books you'll see it referred to h of 0 p. If the null is less than, right? If the null is less than 0.2, then the not the null, the alternative is less than 0.2, then the null would be greater than equal to 0.2. It'd be the opposite, right? But in this textbook, they're just for the null hypothesis putting an equal, okay, for right now. But just know that it's to be the opposite, right? The inequality, but it's kind of equal in it, right? A null has to have an equal equality. So they're just putting it greater than, equal to, less than, equal to, and equal to are the three options, right? Less than, equal to, greater than, equal to, and equal to are your three options for a null hypothesis as far as the inequality. For a alternative hypothesis, H1, here's your three choices, right? They can be less than, greater than, or not equal to, right? Less than is left tail, right? Greater than is right tail, and then not equal to is a two tail, right? Note that these do not have an equal, right? So you look at if you look back at your notes, to be able to tell what type of tail this is, we've got an equal for the null. It's going to be true every time, right? As far as it's going to be an equal. The alternative hypothesis is the P is less than 0.2. Well, if it's less than, then it's a left tail, right? Because greater than would be for a right tail and not equal to would be for a two tail, okay? Now, what parameters being tested? Remember, I told you that there was three. There was the mean, the population, and the standard deviation. We know that this is a population right here. We know that that's correct because of right there. Okay, we got a P, right? If it had a mean or a mu symbol, then it would be the mean. And if it had the standard deviation symbol, then it would have the standard deviation, right? So that's how you'll be able to tell which parameter is being tested. Now, let's look at this. Suppose that the null hypothesis is rejected. Okay, we're rejecting the null hypothesis, which means we're accepting the alternative. Okay, state the conclusion based on the results of the test. 6 years ago, 12.7% of registered births were to teenage mothers. A sociologist believes that the percentage has increased since then, right? So when they tested it, they found that the alternative was greater, right? And this is a population greater, right, than 0.127. So it would be a right tail, right? It'd be a right tail test, and then the null hypothesis would be that it's equal to 0.127, which is really 12.7%. Okay, so they're saying we are rejecting. So we're rejecting the null because we accepted there was evidence to accept the alternative or the claim the alternative hypothesis. Now, so what does that mean? Which of these following conclusions are correct? There's not sufficient, no, because we accept the alternative, which meant, hey, it has increased. So there's sufficient evidence that the percentage of teenagers smoke has remained the same. No, not remained the same. That would be accepting a null hypothesis, right? No change, right? Well, it'd be alternative, but it'd be no change, it'd be two-tail. D, there's sufficient, not significant, sufficient evidence to conclude that the percentage of TMOs has increased. That was our claim, right? So this problem goes back on how do you express your answer, which is the last two examples that we looked at, okay? So that's what this particular problem is dealing with. Any questions thus far? Anybody? Pretty straightforward on the hypothesis testing. The blank is a statement of no change, no effect, or no difference. Well, we know that that's the null hypothesis, right? So that's just to fill in the blank. On this one, the null and alternative hypothesis are given to determine whether the hypothesis is left tail, right tail, or two tail. Well, the null is equal, so that's that. But we're saying that the mean is less than, all right? If it's less than, it is left tail, right? Greater than is right tail. Not equal to is two tail. So it's the left tail. And then we're looking at a population mean because it used mu, okay? If it used P, it would be a population proportion. If it used standard deviation symbol, it would be the population standard deviation. So pretty straightforward on that. You just got to know how to read the null and alternative hypothesis that's stated, okay? All right, so this last one, if a hypothesis is tested at an alpha 0.05 level of significance, what's the probability of making a type 1 error? Well, we said that the alpha was the same as, or same probabilities of type what? 1 error, right? We said that back in the notes. So if the probability of alpha, or the level of significance, is 0.05, then that would mean that there's a confidence interval at 95%, right? At only 5% that it wouldn't happen. And this error would be a type 1 error, right? So the probability of making a type 1 error is 5%. It's the same as alpha, right? The 95 would be a confidence interval, and this is 50%. That's just not moving your decimals correct. And then this is never true right there. Okay, so that's why it's C. So I think that's all for 10.1, looking at a null and alternative hypothesis, being able to write them, being able to know if they're left, right, or two-tail. So any questions on this before we leave 10.1? Anybody? I'll stop and we'll see. So 10.2, we're looking at hypothesis test for population proportion, right? We're going to explain the logical hypothesis testing. We'll test hypothesis about a population proportion. Now we'll go over two types, a classical approach and a p-type, and then I'll show you how to do it on the calculator. Now, I'm not going to go into extensively on the classical or the p approach, right? Because the calculator gives you both of those. So we'll really just kind of touch on it and continue. And I'll show you calculations and point out stuff that you need to just kind of be mindful of and examples with it. We're going to test a hypothesis about a population proportion using the binomial probability distribution. Okay, so basically we're going to make sure that the population has a normal distribution on it. All right, so here we go. The research obtains a random sample of 1,000 people and finds that 534 are in favor of abandoning cell phone use while driving. So the p-hat, right, is our x over n, right? So does this suggest that more than 50% of the people favor the policy, or is it possible that the true proportion of registered voters who favor the policy is the same as is some proportion less than 0.5. And we just happen to survey a majority of in favor of the policy, right? So in other words, would it be unusual to obtain a sample proportion of 0.534 or higher for a population whose proportion is 0.5, right? What is convincing or statistically significant evidence, right? Well, when observed results were unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant, right? When results are not found to be statistically significant, we reject the null, right? So when we accepted the null hypothesis, we'll say that things are statistically significant. Okay, so that's a big word there. All right, so we're going to use this example as we progress through. Okay, so determine if a sample portion of 0.534 is statistically significant. We build a probability model, right? So n times p, since n times p times 1 minus p, and we know that 1 minus p is basically q, right? Is equal to, the n is 1,000, the probability is 50%, right? And then 1 minus 50%. So is it binomially distributed? So yeah, that's greater than equal to 10, right? The NPQ is greater than equal to 10. So we can, and that the sample size n is significantly smaller than the population size, right? We can use the normal model to describe the variability of p hat. All right, so the mean of the distribution of p hat, is the mean of the population of 0.5, right? And the standard deviation is calculated here. Now, this is what we were looking at previous, right? Standard deviation of p hat is equal to the square root of p times q over n, right? P times q over n. So that gave us a 0.016, okay? So if we were to do this, we're looking at, we draw our model down here, and here's our mean, 0.5, right? And if you go up 1, this is plus 1, and this is a minus 1, right? 0.5 minus the standard deviation, and then 0.5 plus it, we get this model. And that's the sampling distribution of the sample proportion, right? So we're kind of looking at where do we stand in the normal distribution. And I highly encourage you to look at these and draw them out, okay? Because it's going to make a little bit more sense when we do that. All right, so we consider that sample evidence to be statistically significant or sufficient if the sample proportion is too many standard deviations, say 2 above the assumed population proportion of 0.5, right? So we call our simple random sample yield a sample proportion of 0.534. So that's the p hat, right? Here's your p hat. So if we want to find a z of this, right? We want to find the z of this. Be p hat minus the mean divided by the standard deviation of the p hat, right? And you get a z of 2.15, right? Standard deviation is above the hypothesized proportion of 0.5. Therefore, using criterion, we would reject the null hypothesis. So what does that really mean? So let's look at the next slide. Why does it make sense to reject the null hypothesis if the sample proportion is more than 2 standard deviations away from the hypothesized proportion? The area under the standard normal curve to the right of z equals 2 is 2.28, right? Did it give us an alpha? I don't think it gave us an alpha on here. Let's go back and look. No. Nope. Okay, then. All right, so how did they come up with 0.0228? Okay, if you look at that, we're looking at, let's see, they would have done, right, because that would be 95, right? This would be 95% down here. So an alpha is 0.5. They really didn't say it, but how did they find this area? Well, if you were to put, when we went here, 2 standard deviations, if you were to go normal CDF and then go 2 is the lower limit, right? 1E99 and then the 0 and 1, we would get 0.0228. Okay, so that's how they're getting this area underneath that curve. Now, how did they get that? Well, they made the assumption that of it being above 2, right? You know, we consider the sample evidence to be statistically significant or sufficient if the sample proportion is too many standard deviation. So they just arbitrarily picked 2, right? Are we going to do that? No, it'll be a little bit more laid out, okay? So if you look at this z-score, you should be able to get this, okay? All right, so if the null hypothesis were true, right, the population proportion is 0.5, then 1 minus that, 0.9772, which would be 97.72% of all sample proportions would be less than half plus the 2 standard deviations, right? Of only 2.28% of the sample proportion would be more than that, right? So we know that this is 0.32, right? This is 0.5, okay? So we got that. And then that's how this comes up. Okay, so right now you're probably going, I don't really, it's not making much sense. It just goes out kind of crazy until you really start to look at it and start to do some of the math, and then we'll look at it on the calculator, which will make a little bit more sense. Speaking of calculator, I need to do this while I'm thinking about it, because I didn't. Here we go. I don't like that. I don't like that one. I want this one. Let's see. I want that. I want this. Give it just a second or so to load up. Then we'll get back. Then we'll start looking at some other stuff. Close. Okay, we'll hit clear. We'll hit really mode. All right. So let me clear this out. All right. So let's get back to 10.2. If the sample proportion is too many standard deviations from the proportion stated in the null, then we reject the null. Again, it's really not making much sense, because what we looked at, we assume, you know, they just kind of threw 2 standard deviations, right? A p-value is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true, right? So we're looking at the p-value. We're actually looking at the area underneath the curve. All right. And that's a probability. Now, hypothesis testing using the p-value approach, if the probability of getting a sample statistics as extreme or more extreme than one obtained is small under the assumption that the statement in the null hypothesis is true, then we will reject the null hypothesis. Meaning, if our p-value is less than our alpha, then we will reject the null, right? But if the p-value is greater, then we would not reject the null. Okay. And when we talk about null and alternative, we talk about hypothesis. Okay. This would be rejecting null hypothesis, right? This statement right here. And then the other statement would be if p is greater than alpha. Okay. So those two representations you might want to make sure that you have down and understand. Did I just move it? I just did. All right. I'm just making some notes here. All right. So here we go. So the logic of the p-value approach. The static criterion we may use for t-testing is to determine how likely it is to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5, right? If a sample proportion is 0.53 or higher, it's unlikely. We have evidence against the statement in the null hypothesis. Otherwise, we do not have significant evidence against the statement. Okay, so they're just kind of looking at from a p-value standpoint. Okay, so again, this is what it's talking about. We can compute the probability to obtain a sample proportion of 0.534, right? Or higher from a population whose proportion is 0.5 using the normal model. And then that's, you know, where did 534 come from? That is p hat. Was it p hat? I think it was p hat. Yeah, I get 534. Yeah, it's p hat. Yep. All right, that's p hat value. So the z on here, you know, whether they come up with this calculation, it's p hat, right, minus the mean of p, right, over what? The standard deviation of p hat, right? That's this. So that's where they come out and they get 2.15. So we compute the probability of p hat's greater than 0.534 is the probability that z is greater than 2.15, which is 0.0158. So the value of 0.0158 is called the p-value, which means about 2 samples in 100 will be given a sample proportion as higher than the one we obtained if the population proportion is really 0.5, right? Because these results are unusual, we take this as evidence as being against the statement in the null hypothesis. Okay. Again, a lot of theoretical stuff, a lot of where's it making sense. So we'll just kind of go through this and you can recall some stuff and it'll make a little bit more sense as we progress through. It's a probability of getting a sample proportion that's extreme or more extreme than one obtained is small under the assumption that the statement in the null hypothesis is true. We reject the null hypothesis, right? So the best point of estimate p, the proportion of the population with certain characteristics, is given by p hat. That's x over n, right? Some number out of the total, right, of the sample, where x is the number of individuals and n is the sample size, right? So we've looked at this before, right? Recall that we're looking at standard deviation of p hat, right? The p and the p hat are the same, right? Mu is p, right? So the mean of the p hat is p, so that's where all this is coming from. P and Q, right? Provided the following requirements are satisfied. If you remember, there's three things, and we talked about this: a random sample, n times phi times q has to be greater than 10. That means that we can use a normal distribution model, and that the sample values are independent from one another. Again, those three criteria for population proportion, right, to be able to analyze and do it under a regular normalized model, I guess would be about the best thing to say. So testing hypothesis regarding population proportion. So we still have these, right? Okay. P sub 0, that's going to be P naught, that's going to be whatever value is in your null hypothesis, okay? So see this, P equals P naught across here. And you're just looking at the same thing as what we looked at before. If it's not equal, it's 2tail. If it's less than, it's left. If it's right, then it's P, right? P naught assume the value of the population. So step 2, select a level of significance and alpha depending upon the seriousness of making a type 1 error, right? So let's look at a classical approach. Now this is looking at a Z, okay? Z naught's P minus P naught divided by the basically standard deviation, right? Standard deviation of P. Here's your critical, alpha divided by 2. Like if we said that this was 95% here, then we would have 2.5% here, and we'd have 2.5% there. That's what that alpha divided by 2, right? Critical down here, left tail, and then right tail. We can 1 minus the area, right? Or we can look at it. You just got to make sure you're up here looking at this, because the Z table is going to give you area to the left, right? So you need to do 1 minus to get to that. So just kind of be aware of that. Here it is in looking at it in terms of Z. And it's saying if it's in between, or if it's less than that or greater than the other, then we'll reject the null, meaning it's in, right? Z naught is less than negative Z alpha, and if Z naught is greater than Z alpha, we'll reject. So here's the conditions for looking at it from a Z naught, okay? And that's comparing critical value of the t-test statistic. Again, your calculator will give this to you. I mean, so it'll give you P and the Z. So we'll look at it. If we look at a p-value approach, then the Z naught, we're looking at it here. And it's just saying the same things, right? They're doing the standard deviation of that, right? So because this, whatever's here, this value is going to be the same, right? Symmetry on the Z's. Step 3, use it, and then if p-value is less than, we'll reject it, right? And then state the conclusion. So that's basically what we're going to do. But we're going to look at it. The first example is going to go through the classical approach, right? We'll see the formulas and how everything is there. So in 1997, 46% of Americans said that they do not trust the media when it comes to reporting the news fully, accurately, and fairly. And that was in 1997. Wow, there's more now. In 2007, 1,010 adults nationwide, they polled 1,010 adults nationwide. 525 stated that they did not trust the media. And at an alpha of 0.5, remember that's your type 1 error, level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since then? So if we look at this, we got to first, we want to know, here's our claim, if is there evidence that the Americans, the percentage has increased, right? So it's increased from what, 46%, right? So if we look at this as a null hypothesis, we're going to say P is equal to 0.46, right? And then our alternative hypothesis, H1, sometimes you see it as HA, okay? So just be aware of that, H1 or HA. P is greater than, right? So we're trying to see if there's enough evidence that we can say that there's enough evidence to support the claim, which would be the alternative hypothesis, right? So that we can reject the null, right? Saying that it's still the same. So we've got to go through these three steps, right? Is it simple random sample? And it is. Is N times P times Q? Well, P naught, N is 1010, P naught is 0.46, right? It would be the same. It's right here, P naught, and then 1 minus that. So we get 250.9 is greater than 10. Okay, so we can do this. We can treat it like a normal distribution, right? And since the sample size is less than 5%, then assume that the independence is met. So those are the three things. And normally we just do the second one, right? And then we consider the third one a little bit. But as we're looking at this, it's important to know that here's the null hypothesis and alternative hypothesis. So let's kind of look at this. All right, so we've already said it. We've already said it, the null hypothesis. Here's your null, right? Here's your alternative. And we've already written them. Its level of significance is 0.5. They're looking at p hat because it's 525 over 1010, right? And then the test statistic is Z naught of 0.52. That's p hat minus the mean, p, right? Over the standard deviation of p, right? And I guess they just do this right here is P or P naught right there. And you get 3.83, okay? Now, you go, well, how do I do that if it's, how do I come up with a z-score or z naught if it is, on the calculator? Well, we have our information here. Let's go and look at our calculator. So what we're going to do is we're going to do stats. And if you look in here, it says test, right? So we're going to arrow to the right, or you can arrow once to the left or arrow twice to the right to get to test. And we're going to do a 1 proportion z test, right? Which is number 5. This is everything that we're doing. Now, we said that P naught was what? The P naught was 0.46, right? Okay. Our X value, well, our X value is how many of them made this claim, right? 525 stated, right? Out of 1,010. So 525 out of, guess what? 10. So those are the three things that we have to put in, right? Our P naught, our X value, how many out of the total sample population, right? How many of the population said this, how many claimed, and then out of how many. So our next thing is we're going down to what type of proportion. Is it left, right, or 2? And if you remember, it's a left tail because P is, well, no, it's a right tail because P is greater, right? So the P is greater than P naught, right? So we would make sure that this would be, if it was not equal, that'd be a 2 tail. This would be if it's less than. This would be if it's right, greater than, right? So we make sure that that's highlighted, and then we come down, we can draw it, right? Or we can calculate it. Now, we're going to calculate it, but I'll show you. Let's do draw. I don't have, I've got something, I got second stat plot somewhere. I got something on that didn't like. Let's see. I'm gonna hit 1. Yeah, I got my stat plots on, so I need to turn them off. 4. All right, so if we go back and go stat, arrow over 5, all of our information should still be there. I want to see this. I guess I should have done it before. We'll see if we can get it to draw. All right, so there you go. It should shade. Oh, I bet you I didn't do something. Itchy. Well, here's our Z, 3.813, okay? And then our P value is 1e to the negative 4, which is really, really, really small, right? So I want to go back and do that so that you can see. Let's see if it's the one I done earlier. Okay. It drew the area, so no, it's just going to do that. Unless it's just, it should be drawing unless it's just up here and we can't see it. We'll go back and let's do Z and we'll do 5. Instead of drawing it, we'll do the calculate and then we'll talk about what it gives here. All right, so it gives us critical Z, right? Z naught 3.8133 is what it's calculated. On the previous example, on the example that we're looking at, it was 3.83, right? All of this is coming off of that. So we calculated 3.813, okay? And then if you look at the P, right, that's 6.8587 e to the negative 5. So, and you can see the proportion P is greater than 0.46 P naught, right? It gives you P hat, and if you calculate P hat, it was 0.52. They rounded, so that's the little bit of difference. This is not rounded, okay? Well, it's rounded to 4 as opposed to 2, okay? So we've got that. Now, what is it given? So since that is the right tail test, we can determine that the critical value at alpha of 0.05 level of significance to be 0.05, right? Well, where did they come up with this? Where did they come up with this right here? This 1.645 should look familiar, right? That is a confidence interval. It's the area under it for 95%, right? Confidence area. It's the area, right? It's the Z score, right? 1.645, right? So that's where that came from. Remember I told you to make a table what your confidence intervals are and then the area. So if you have that, you should see that your Z is 1.645. Step 4, since the test statistic Z naught is 3.83 is greater than the critical value of 1.645, then we can reject the null hypothesis, right? So this, and if we look, the next one, maybe it's, let's see if it shows it. We'll do it here. So basically, we're doing this. We had a Z, what do we say, of 1.645, right? That's a 95% confidence interval, right? That'd be what the area is for that. And then here's the alpha, right? So if we're looking at that, we got a critical Z naught of being 3.813 something. That's over in here. And if I can get a, yeah, it's over in here somewhere, right? So it's in the claim, right? Our claim was it's greater, right? So yeah, it came out that it was greater in our area that we're wanting to look at, to be able to accept the claim, right? And not reject it. So we can accept the claim, we can reject the null, right? We can reject the null. Okay. Now, so that's where this number and this number comes in. Those are all Z scores, right? And if you look back here, it said that Z naught was greater than the critical of Z. I wish I had that. Okay, here it goes. So since we'll look at it from p-value, since this is a right tail test, the p-value is the area under the standard normal distribution to the right of the test statistic Z naught 383. That is, the p-value is equal to the probability of Z being greater than 3.3 is approximately 0, right? Since the p-value is less than the level of significance, we reject the null hypothesis. Now, how do we know that? How do we know it's approximately 0? Well, this is 6.87587 e to the negative 5, which if you move that 5 spots to the left, then you're really dealing with a p-value, the p-value of 0.00006, right? That's what you're saying. That is less than our level of significance, which I think was 0.05, right? So we can reject the null. Okay. So, so there is significant evidence at the alpha of 0.5 level of significance to conclude that the percentage of Americans that do not trust the media to fully report has increased since 1997. Okay. So two things we can look at. We can test it and look at it from a Z standpoint, which is the classical approach, or the p-value. I think it's easier to look at the p-value myself because they're majority of the time they're going to give you an alpha, right? And you can just check it against your alpha, right? P is less than alpha, we reject the null, right? And that's what we did. We wrote that down a couple of slides back. Okay, so we did this on the calculator. Okay, remember that. What did we type in? With stats, we go left or we can go right twice, right? Doesn't matter. You want to get the test. You want to do number 5. And then we put our P naught, our X value, right? Our N, our number from our sample. We determine if it's two tail, left tail, or right tail. And then we just said calculate, right? And when we do that, it's going to test our claim, right? And tell us, it's going to give us our Z, our critical Z, or Z naught, right? So we can compare Z values if we want to by the classical approach, or we can look at our P value and compare it against our alpha. And it's probably better just to take the P value against the alpha. All right. So any questions on that? That's one example. They did the calculation. I showed you how to do it on the calculator, what each one of those means. Okay. Go through some stuff. We may cull out a little bit because some of the stuff's kind of redundant. A two-tailed hypothesis testing is using confidence intervals. 1 minus alpha. When testing the null hypothesis, P is equal to P naught versus H1, P is not equal. It's a two-tail, right? Times 100% confidence interval contains P naught. Do not reject the null hypothesis. However, if the confidence interval does not contain P naught, conclude that P is not equal to P naught at the level of significance alpha. Okay. So if you're doing a two-tailed hypothesis test, testing using confidence intervals, then you're not going to reject the null, right? but we're going to leave the confidence interval that does not contain the P naught, conclude that P is not at that significance level, right? So I don't think we have any. Most errors are dealing with alphas. Okay, so they're kind of throwing out everything in the kitchen sink when they're going through this. Okay, for sampling distribution of p hat to be approximately normal, we require the n times p times q to be at least 10, right? Greater than or equal to 10. Now, what if this requirement is not met or satisfied? We stated that an event was unusual if the probability of observing the event was less than 5%, right? This criterion is based on the p-value approach to testing hypothesis. The probability that we computed was the p-value. We used the same approach to test hypotheses regarding the population proportion for smaller samples. Okay, it's just saying that we're going to state whether we reject or not, but we're going to basically say that the event was unusual, because if we have something, if it's, was it less, if it's less than 5%, it's an unusual outcome, right? Or unusual event, meaning it probably is not going to happen. So, all right, so we're looking at this. Is this the one I want to? Yeah, it is. Okay, so we're going to check. We're going to pass on this one. You've got it. It goes through. We ain't got to worry about it. Okay. All right, so that's basically hypothesis testing, but we're doing a one proportional z-test. Okay. So let's kind of look at what our homework's going to give us, because the homework's going to give us a lot more simpler things. Okay. So we're doing a one proportional z-test, right? Now, how do I get to it? So I go stat, right? Then I go test, and then I go number 5. Okay, so there's a list of things that we got to make sure that we put in. P naught, X, N. We have to tell whether its proportion is what. If it's two tail, left tail, right tail, and then we'll hit calculate, right? Okay. So on this, let's kind of look and see if we can pull this and tell what things are. So they tell us that here's the null. P is equal to 0.7, right? That 0.7, that's the P naught. P is equal to P naught versus H of 1, where P is less than, right? See this right here? It's less than, then it is a left tail, right? Okay, so we're going to do that it's less than P sub 0, right? Now P sub 0 is 0.7. Okay, they give us N, they give us X. They say X is 95 out of 150 people, 95, right? With an alpha of 0.1. Okay, so we're going to look at the alpha. We're going to look at a p-value. Okay, so we are that's 150. Okay, so what we're going to do is, those are the things I've got to have, and those are the steps for getting it. We're going to go and type this in, and then we'll look at it, what it comes out, right? We'll verify that it comes out to a p-value of 0.0374, right? So we'll go here, and we'll go ahead and clear this out. Okay, so we'll clear this, or stop, I guess. All right, clear, and so we'll go stats. You can arrow to the right, because it's it just kind of if you keep going right, it just wraps around and keeps going. So it's cyclical. Okay. Or I can go one left or two to the right. I want to hit number 5, a one proportional z-test. Okay. So when I hit that, I get I got to type in my data. That's P naught 0.7, right? You'll find that in the null hypothesis. There is 95. X is 95, right? And our number that our sample was for sample proportion was 150. Okay. Now, did we need to check some things? Well, in PQ, we could, right? See if it's greater than or equal to 10. On these, they are. But just be aware you need to check that. Now, what's blinking right now is a 2. This would be, if it's greater than, that'd be a right, and then this is less than. We want to make sure we're on a less than because that'd be a left. And then we just calculate, right? So when we calculate, we get a p-value, right? What did I just do? Did I type it all in right? Or did I not type it all in right? 95, 150. Did I do that right? I bet you. 95, 150. Minus. Oh, I grabbed the wrong one, didn't I? I did. Look at that. There it is. I did greater than. Thank you. Because I was like, man, that's not coming out what I'd already done. So let's do it again. Thank you. Good catch. So please be aware of that. Okay. So come down. It's the middle one, right? Less than, right? Okay. Not greater than. So if you, yeah. So looking at this, it's two tail left and then right. Okay. That's how your calculator is set up. Two left and right. And then calculate. So if you pick the wrong one, it's going to give you a wrong value. Okay. So you got to make sure which one it is. All right. So we got a p-value of 0.0374. Right. Does everybody agree with that? Here's our critical Z for our classical approach, right? 0.0374. Now let's go over here. That's what we got our p-value. Okay, now is p less than alpha? If it is, then we can reject the null hypothesis. Well, they said this level of significance was 0.01, and we got a p-value of 0.0374. Okay, is it less? I'm going to change colors. Is it less than the alpha? Well, no, it's not. If it was, if this was true, then we would reject, right, the null hypothesis, if that's true. But it came out to be a false, right? 0.03 is greater than that, right? Then we will not, right, reject the null hypothesis, right? Because it came out to be a false, right? So since p-value is greater than, right, the p-value is greater than alpha, then we will not reject the null. Okay. So does that make a little bit more sense? I know it's kind of like you're going through this and it's kind of like which value, because they keep switching between classical and p-value approach, but our calculator give us both. Okay. So it just depends on how you want to do it. Okay. How you want to set it up. So any questions about this one? Anybody? This is only our first example, and there's only two more. So, and for the 10.2, on this one, is n times p naught times 1 minus p naught, is it greater than 10? Okay, so n is 125, right? The p naught is 0.6. How do I know p naught? It's on your null hypothesis, right? And then 1 minus that. Is that greater than or equal to 10? Well, that comes out to be 30. So yeah, 30 is greater than 10. So yeah. Okay. Now, looking at this again, they've already given us both hypotheses, the null and alternative. We need to determine, looking at the alternative, whether it is a right or two left or right. And this is a p is greater than, so it would be a, guess what? A right tail, right? Now, why is that important? Well, when we do the one proportion z test, we're going to make sure that we're going to choose the correct tail, right? Because if not, we won't get, guess what? The p-value, right? Now, let's do this. I know it's 6:26, but I want to be quick. And there's only one more example out of this, so if you can, hang with us. Okay. So again, stat, 2 arrows to the right or 1 to the left, doesn't matter. You want to get to test. We'll hit number 5. Now we had a p naught of 0.6, right? We had an x value. They said the x value was 85. Okay. And then they said that n was 125. Okay. Now, greater than. Here's your right, here's your left. I mean, two tell left and right. We'll make sure we get the right one. And then we come down here to calculate. Bada bing, bada bing. And ladies and gentlemen, if you round this to three places, their p-value is 0.0339. Three places be 0.0334. Okay, right here. So what we're going to do is we're going to take that p-value, and it's easy to do it on the p-value, okay? We're going to look at this, and we're going to say, okay, what do they tell us the level of significance? Here's our p, and here's our alpha, and we got a p-value of 0.034, and we got an alpha of 0.1. Well, guys, the p-value is greater, right? If it's greater, then we're going to reject it, right? Reject the null, because the p-value is, whoa. Oh, my bad. I'm sitting here not reading decimal places. That is 10%, right? And that's 3%. So yes, it's less than, right? So we would reject, we would basically accept the alternative hypothesis claim that it's greater than 0.6, right? And we would reject the null, right? So reject the null because p-value is less than alpha. Okay. Any questions about that? I want to show this last one, and then I'll take any questions, whatnot, and everything. And your problems are going to change. Okay. You may have a left tail, right tail, or two tail. Just note that they're going to give you everything in here, right? This is everything that they're giving you. So we're not having to calculate anything, nor read it from a problem yet. Okay. We still got 10.3 to come. And then 12, right? Chapter 12. So one more section in 10, and then chapter 12. So here, you know, is it? Yes, if you do your calculation, it's 150 times 0.61 times 0.39. Is it greater than or equal to 10? Well, 35 point something is greater than 10. Okay, so yeah, that checks out. So our P naught, we know our P naught is 0.61. We know our X is 87. Okay, and then our N is, guess what, 150. Now, when you put that, and this is for a left tail. How do I know it's left tail? See that? P is less than, it's left tail, right? So, you know, it's either going to give us this, or it's going to give us this value, right? So let's kind of look at it. What's happening? Which one's true, right? A p-value of 0.226. Is it less than, what's our level of significance? 0.01? No, that's a false. This is a true, right? If this was true, if this statement right here was true, then we would accept alternative hypothesis, right? But because the p-value 0.226 is greater than 0.01, right? It's greater than, then we're going to not reject the null hypothesis because p-value is greater than alpha. And I guess you just put it and see which one is greater than compare, right? You've got these statements right here. I guess see which one, right? And this is true. This is greater than this. So that would mean that you don't reject the null. There's not a significant claim to accept whatever their, or significant evidence to accept their alternative hypothesis, right? Their claim. So we're not going to accept the null. We're going to not reject it. Okay. So that's the big key points that you have to take in consideration.